Good day, everyone. My name is Lawrence A. Cornelio, a BSEC 3 student from Bicol University, Pulangi, and today I will be discussing my laboratory activity 6, which is sampling and aliasing. Now, first, we import NumPy for mathematical operation, and we import matplotlib for plotting. Then, now we set our F signal is equal to 5, representing a 5 Hz sine wave using NP.line space 0, 1, 1000, we create 1000 points between 0 and 1 seconds. This then sampling makes the signal appear continuous. Then our continuous signal is x is equal to np.sine 2 times np.pi f signal times t. So we plot this in blue as our reference signal. So here we plot the signal. We have the plot, tx label continuous signal. We have the title. For the title continuous time signal, 5 Hz sine wave. Then we put the x label time. Then y label amplitude. Then press the speed. Press the legend. Press the show. Now setting the sampling rating. Now we define our sampling rating. So fs high is equal to 50 Hertz means we take 50 samples per second. So according to Nyquist theorem, to avoid aliasing, we need to sample at least twice the signal frequency. So our signal is 5 Hz, so minimum sampling rate is 10. Since 15 is well above this, so now we put the Fs low to 6 Hz. So this is below the Nyquist rate of 10 Hz, so this will cause aliasing. Now, so we create the time vectors. So first is n high, so np dot range 0, 1, 1. FSI, so this generate time points from 0 to 1, spaced by 1 divided by the sampling rate. So for 50 Hz, spacing is 0.02 seconds. For 6 Hz, spacing is about 0.1667 seconds. Then we sample our sine wave this time at this time points using np dot sine. So np dot sine to pi times f is signal, which is 5, then n high. So for then now we create the new figure is the figure with PLT. The figure, fig size 12.6, so 12 inches wide and 6 inches tall. Then we use PLT the subplot 211 for the proper sampling example and PLT subplot 212 for the undersampling. So the 211 is for the 50 Hertz and the 212 is for the 6 Hertz. So we put the PLT the plot, continuous signal, with this time N high, X high, line FTR, so on. So PLC title, proper sampling, which is there is no aliasing, X label time, Y label amplitude, PLC grid, 11. So the second one is subplot 212, continuous signal. So here is the PLC title under sampling at F is low. So this part has aliasing, then X label time, Y label amplitude, PLC grid. Nah, so in the first subplot, we plot the continuous sine wave as reference, then we overlay the sample using the stem, the red marker, and red lines. At 50 Hz, we have 50 samples per second. Notice how the sample captures sine wave accurately. Then, when we connect this sample mentally, they perfect track the original wave for tau as times 1, so we can see. uh, this. So this was the continuous signal, 5 Hz, and so this was the proper sampling. So as you can see, the proper sampling look like the original sine wave. Then second subplot is under sampling at 6 Hz. So as you can see, the second subplot, we are going to show the continuous sine wave in blue. Then we overlay the sample taken only at 6 Hz, so using green. So this part. So as you can see, this does not look like the original wave. So the sample are too sparse to capture the true oscillation. If you connect this green sample, they would form a much lower incorrect waveform. This phenomenon is called aliasing. The high frequency 5 Hz appear as a false low frequency signal. So, understanding why aliasing happens. So, aliasing occurs because we violated the Nyquist criterion with 6 Hz sampling only. We take only 6 samples per second, but our original signal oscillate 5 times per second. So, the sample cannot distinguish between the true 5 Hz signal and the lower frequency signal. In fact, 5 Hz signal fallbacks or alias to a 1 Hz signal. This is why green sample appears to trace a much slower wave. So, that's all. Thank you.